So let's analyze how this amortizing of data movement over computations works. Okay. Here I have indicated what the sizes of the different submatrices are, where the sub C means that we're blocking for caches. Right? Now, how much data, when we just focus on this one multiplication with blocks, how much data needs to be brought into cache and brought back out of cache? Well, MC times NC doubles need to be loaded from C. MC times KC doubles need to be loaded from A. And KC times NC doubles need to be loaded from B. And then finally, when the computation is done, the block of C has to be written back out to main memory. So we'll just put a 2 in front of that. That's the number of doubles that need to be brought from main memory into cache and then back. Right? Now, how many floating point operations do we perform with those doubles? Well, we know that a matrix-matrix multiply is equal to 2 times m times n times k, except now m is really m sub c because we're using a subblock, submatrix, k nc and kc. So that's the number of floating point operations we're performing. Now, just for analysis sake, let's analyze what happens if these block sizes are all equal. Let's call it B. All right? Then what we see is that the number of floating point numbers that need to be brought from memory into cache and back is 4 times B squared. And the number of floating point operations that are performed with those numbers is then 2 times B cubed. Or maybe we should switch that around. We're doing 2 times B cubed floating point operations for the 4 times B squared memory operations that are being performed. Okay, that's the ratio. And what you recognize is that if B is large, then you're going to end up spending most of your time in floating point operations and relatively little time in memory operations. Okay? So, the idea is block it so that B is large enough so that you can offset the cost for performing the memory operations with floating point operations that really represent the useful computation.